Good morning. Today we're going to talk about liquids, in particular vaporization, vapor pressure, and then we'll talk about sublimation and fusion. Okay, vaporization is the same thing as evaporation. It's the escape of molecules from your liquid state to the gas or vapor state. Condensation is actually the reverse, going from the gas state to the liquid state. When this happens, basically, as we know, some of your molecules in the liquid state will have energy enough to break the surface tension and escape into the gas state, leaving the molecules that have lower energy behind. If you look at the rate of vaporization, it increases with temperature. So on hot days, you have a puddle of water, it actually evaporates faster. It increases in surface areas. So if you spill water, then if you spread it out, it will evaporate more quickly. Okay? And it increases with decreasing strength of intermolecular forces. So you have less of a surface tension. So in this case, if you compare water, a puddle of water, to a puddle of gasoline, the gasoline will actually evaporate at a much faster rate than the puddle of water. The energetics behind vaporization is basically this. It's endothermic. A liquid needs to absorb energy in order to get into the gas state. Okay? For water in particular, that amount of energy is 40.7 kilojoules per mole of water. Okay, to go from the gas to the liquid state in condensation, the delta H is a minus 40.7. So the reverse will just give you the opposite sign. But we're just going to talk about vaporization. When you hear condensation, you know it's just the reverse. Okay, let's talk about vapor pressure. Now that we know what vaporization is, going from the liquid to the gas state, when we talk about vapor pressure, you have a sealed, closed system, not isolated. It's closed, so I can't exchange matter with my outside, with my surroundings. And what we find is that right now, when we first seal it, and this is a vacuum, you give it some time, and suddenly we get to the point where it's in this equilibrium. The number of water molecules going into the gas state is the same as the rate of the molecules going back into the liquid state. When this reaches this dynamic equilibrium, and usually we'll talk about it from now on as equilibrium, but just so you know, if I follow this particular water molecule, it won't always stay in the vapor state. It may go back into the liquid state, and then it may go back into the gas state. But on the whole, when we say dynamic equilibrium, the number up here is steady, the number down here is steady now. We call this the pressure exerted by the gas, okay, vapor pressure. What's typical is that since it's vapor pressure, this will increase, the vapor pressure increases with temperature, okay? And for pure substances, we often will look at the vapor pressure. You have lookup tables. We have lookup tables for the vapor pressure of water at the various temperatures. Okay, so we talked about vapor pressure, and it's independent of the amount of liquid or vapor present. So if I had a very tiny container versus a very large container, once it reaches equilibrium, then the vapor pressure will be the same regardless of the size. Okay? And we said before, with any pressure, you know that it's going to increase with temperature. So here, how do we measure it? So remember, when we have our container with the gas, okay, we attach what we call a manometer. And as you can see, if the pressure inside is the same as the pressure outside, my manometer, the two levels of mercury is the same. As I increase my vapor pressure on the inside, because I'm getting gas from the molecules leaving the liquid state, going to the gas state, once it reaches equilibrium, then it exerts a pressure that's greater than outside, and the difference here is basically my vapor pressure. And that's how we can measure vapor pressure. Okay? So in this chart, right, if they evaporate easily, right, so look at this. This is minus 30 degrees Celsius. You can see the vapor pressure is almost 1, right? At minus 25 degrees or so, the vapor pressure is 1 atmosphere. Okay, so the methyl chloride, because it evaporates readily, it's called volatile. Okay, so these guys are volatile. Because you see, even at 0 degrees Celsius, these guys already have, this one, like butane, has a substantial vapor pressure. Okay, as you go across, like the 2-heptene, you can see that at 40 degrees, there's very little vapor pressure present. So 2-heptene is considered much less volatile. Okay, and here again, we show all these different substances, and you can see here's 1 atmosphere at 760 millimeters mercury. Okay, so at, let's say, 100 millimeters mercury, diethyl ether, okay, this is diethyl ether, not diether ether, right? Already at 0 degrees and at 100, at 0 degrees, diethyl ether gives you almost about 200 millimeters mercury vapor pressure. So diethyl ether is considered very volatile. Okay? If you look here, to do the same thing, I have to, for mercury, I have to be almost at 300 degrees Celsius. So mercury is considered non-volatile. Okay? So volatile, as I go across, becomes non-volatile. Now, when we talk about boiling point, the definition of boiling point is the temperature at which the vapor pressure of a liquid is equal to the external pressure of the liquid. In other words, suppose I'm at sea level, I'm at 760 millimeters mercury. Then the boiling point is right here for diethyl ether, which is like a negative, actually let me see my chart. This is 0, this is 50. No, this is about 37 degrees, okay? 34 to 37 degrees Celsius, okay? So if I said, well, what's the boiling point for diethyl ether at 300 millimeters mercury? So you go to 300 millimeters mercury and you say, well, the boiling point here is that it's about maybe 10 degrees. So you see a substantial drop in your boiling point when my pressure drops. Likewise, let's talk about water. Here's water at sea level at 1 atmosphere, 760 millimeters mercury. And this is 100 degrees. Oh, good. Now, suppose I was on a plane and I was down to, let's say, 600 millimeters mercury. Okay, the boiling point of water now is no longer 100 degrees because 100 degrees is this white line. The boiling point of water at 600 is less. So it could be like 90 degrees. If I went all the way down for water, which is blue, if I went down to about 110 millimeters mercury, you can see the boiling point of water drops down to almost 50 degrees Celsius. So we make use of that. So if you wanted to boil a liquid, but you're worried that it's sensitive to high temperatures, by putting it in a vacuum situation, we can decrease our boiling point so we can easily remove a liquid from a solution based on a much lower boiling point and not have to worry about decomposition at high temperatures. So that's one way we actually use the fact that the boiling point is the temperature of the liquid. It has to be equal to the external pressure of the liquid. But when we talk about liquids and we say, listen, I want to know the boiling point of water. Now, we don't know, I want to know the normal boiling point of water. But when we talk about our normal boiling point, we have to define at what pressure. So a normal boiling point is the boiling point at 1 atmosphere, which is standard pressure. So anytime you have 1 atmosphere and you look at the boiling point where it intersects those lines, those are our normal boiling points. Okay. Another factor we need to take into account is called critical point. This is where vaporization of a liquid, okay, in a sealed container. And what happens is when we have a container, you can see two phases. You can seal the container, and what we're talking about is you see your liquid state and you've got your gas state. When we hit critical temperature, suddenly you can't distinguish between your liquid and gas. It has the properties of both. Okay, so when your temperature is greater than critical temperature, you have one phase. You don't have two phases. And the critical pressure, okay, is the pressure at which this transition occurs. Okay, when we get to phase diagrams, we'll take a look. We talked about vaporization, which is a liquid going into the gas state. Sublimation is when a solid goes into the gas state. Here's your example. This is dry ice. This is solid carbon dioxide. It goes directly into gas carbon dioxide. It does not go into the liquid state. If I go from a gas directly to a solid, I mentioned it earlier, but I want to mention it again, it's called deposition. Okay, and it goes here is like iodine. And what iodine does as a solid, okay, is it turns into the gas state. There's no liquid here. It turns directly into the gas state. And on a cold finger there, it starts resolidifying. So what's happening is the gas is going directly into a solid. And this is called deposition. Okay? What are the other terms? Fusion or melting. Okay? Opposite way is freezing. So freezing is liquid going to solid. Melting or fusion is solid going to liquid. When I'm going from a low energy state to a higher energy state, it is endothermic. It needs to absorb energy. How much? In this case, to melt it, 6.02 kilojoules per mole of water. Okay, this is called a heating curve, and we'll talk about this in more detail. And note that the temperature is constant whenever I change a state. Here, the temperature is constant. There's no change in the temperature, okay, because all the energy that you're putting in there is to convert it from one state to the next. If my state's constant, notice as I add in more heat, it increases the temperature. Okay, so here's your overall relationship between your states. This is the enthalpy of my system. Solids, they don't really have a lot of energy in them because they're held in a 3D orientation, okay, 3D geometry. And so a solid is the lowest of the energy states, then liquid, then a gas. So solid going to liquid, that's called fusion or melting. Liquid to solid, called freezing. Liquid to gas, it's vaporization. Gas to liquid, it's condensation. A solid to a gas is sublimation. Gas to a solid is deposition. But one thing that you should know, if I'm going from a solid directly to a gas, then following Hess's law, the amount of energy that's required is the same as adding solid to liquid, then liquid to gas. Okay? And the opposite, the amount of energy that's released is the same as gas to liquid plus liquid to solid. And that would be the amount of heat you need for deposition, or released on deposition. Okay, let's take a break here, and we'll start talking about heating curves for water.